So in this Colab, we are going to build a graph neural network for a molecule property prediction problem. And we are going to use this MUTAC dataset, which has 188 graphs in it. And in each graph, we have the atoms and bonds. Atoms have these one-hot encoding, which has 7 different values, and bonds also have a one-hot encoding, which has 4 different values. And there is a graph level label feature, which is for a binary classification problem. It is only 0 or 1 and specifies the mutagenicity of this molecule for a specific bacterium. So here first we install the Tensorflow GNN pip package, and then we import all the libraries that we depend on, and we download the MUTAC dataset, which has the train and validation labels already split it into 2, and they are in TF record format. And in total, we have 188 graphs in this molecule dataset. So now first step is declaring your graph schema. So here you can see a relation diagram for this dataset. We will use, there is the atoms, which is the node set, and we have the bonds, which is the relation among them. Both of them has a hidden state feature, and these are one-hot encoding features. Atoms feature has like 7 different values, while the bonds can take 4 different values. And we have a context level, graph level feature, which is the label that we will use for training our model, and that is a scalar value that consists of only two classes. So now let's declare the graph schema protocol buffer. Here we have the label feature for the context, which is a scalar feature, so we only specify its type. Then comes the atoms, which is our node set, and it has the hidden state feature. We know that it's a one-hot encoding with 7 different values, and so it's a fixed dimensional feature with size 7. And we have the adsets, which is the bonds, and it is a relation between the atoms. So we mentioned there is also a feature for these bonds, and that's the bond type, and we will represent that as our hidden state feature. So we can use it for TF-GNN layers. And it is also a one-hot encoding, takes 4 different values, so it's also a fixed dimensional feature with size 4. So now that we have implemented the graph schema, we can use this create graph spec from schema PB API, right, to get the graph tensor spec. We are going to use the graph tensor spec to parse our serialized TF examples into graph tensors, and we will also use it for our model layer, the input model layer. So now that we have the graph schema declared and the graph tensor spec generated, here we are using the TF record dataset from the TF dataset API to read the TF records from the specified train and validation paths. And we use this map function to map each individual TF example into graph tensors. And let's see how we do that. So in the decode function, first we use this TF-GNN parse single example that we mentioned in the presentation. So the parse single example takes the graph tensor spec and the serialized TF example representations, and we return us the graph tensor spec. Sorry, graph tensor itself. And there is a label feature in the context. We would like to remove that from the graph before we start training, so we can feed that separately into our model for the prediction head. So we pop out that feature and return the graph and the label. So now let's take a look at one of the examples, right? We can use the TF data datasets, take one and get single element to look at a graph tensor. So let's first take a look at this atoms node set. Atoms node set consists of features and the sizes tensor. So features is a dictionary of tensors with the hidden state and any other features you might have being the key in the dictionary. Sizes shows you will tell you the number of nodes in the node set. So we can see value 14 here. So there's 14 nodes in this node set. And let's take a look at our hidden state feature. Here you can see it's a dense tensor with shape 14,7. So the first dimension, right, 14 is the number of nodes in our node set that we already know from the sizes as well. And 7 is the dimension of the hidden state that we have configured in our graph schema. And you can see here that these are all one-hot encoding features. So now let's take a look at our bound edges. This is normally an undirected relation. Question, go ahead.
Sorry, that 14/7, what is actually represent? Because I think the 7 represent the carbon and other atomic things involved there, but what's this 14 represent?
Oh, sorry. So basically 14 is the first dimension, which is the number of nodes in our node set. So we can, I also mentioned that this sizes tensor tells us the number of nodes in the node set. So you can actually index into this tensor with the node that you are interested in and find out its feature. And each feature has like 7 dimensions, so you can access the full tensor representation of the hidden state.
And what each node represent? Is it like molecule or is it like that? It's an atom.
Yeah, it's an atom, right? So these are the atoms of the molecule. So each graph is a molecule, and we have nodes, which are the atoms in the molecule. Sure. So for bound edges, this is an undirected relation. But in the graph tensor, we have the edges represented as directed pairs, right? So how we worked around this is we actually also store the edges in both directions in the edge set. And in the edge set's graph piece, we also have this adjacency structure. So now let's take a look at the adjacencies, source and target tensors. So we mentioned that there is the node IDs in these tensors that are pointing to the nodes in the node set. So this adjacency, this first code block is looking at the source tensor, and it has a shape 28. So 28 is the number of edges in the edge set, and the respective endpoints, right, can be for the source tensor can be found in the target tensor. And you can see these are also node indices with the shape 28, denoting the number of edges in the edge set. And we also had the hidden state to represent a bond type in the bonds edge set. So let's take a look at that. In the hidden state, you can see the shape of this tensor is 28,4, right? 4 is the fixed dimension that we have specified earlier for the hidden state of the bond type. And 28 is the number of edges. So basically here we are keeping the hidden state feature for each edge in our edge set. And there is also the context, graph context, and you can see it's represented using features and sizes as well. And the sizes tensor here is, as you can see, has only value 1. This is going to be consistent because we have only one context per graph. And the label is a binary class indicating the mutagenicity of the molecule, and it's either a 0 or a 1. So now let's continue with the training. Before we start our training, we have to batch the data sets. Sure, question?
Yes, is it possible to show a visual thread instead of just the nodes?
So we have some tools. If you are interested, we can help you with that. But right now it's not open source, right? And let us know. We are very looking forward to help you out, and would love to give you something. Sammy wants to add.
So Brian wrote like some way to go from this graph tensor to graph in this format that would display here on the Colab, and maybe this is a feature request for push this code so that everyone can use it. Thank you.
So So let's look at the model. First we batch our data, right? Here the batch size is specified to be 32, and we are going to build our GNN model using the Keras functional API. You can also play with some of the hyperparameters here and some of the parameters and see how it affects the model performance. So to build our model, first thing we do is we declare this input layer, which requires a tensor spec, and we have the graph tensor spec, right? We have generated earlier from the schema. So we are going to use that while we call this function. And as soon as you get the graph tensor, first thing you have to do is call this merge batch to components API. This is because TF-GNN expects scalar graphs. TF-GNN Keras layers expects scalar graphs, and merge batch to components will merge the graphs in your batch into a scalar graph where each different individual graph now becomes a component of this one scalar graph. And we also use these map features Keras layer to initialize our hidden state features for the add sets and node sets. And for that, we use the set initial node state and set initial add state callback functions. Both of these callback functions is just applying a linear projection of the hidden state tensors. But for our context features, we want to add a brand new feature. So how you do that is via this replace features function. And for the context, we would like to represent or keep the number of atoms, which is the number of nodes, and the number of bonds, which is the number of edges, in the respective graph. So we already, looked into these sizes tensors, which keeps track of the number of nodes and edges, right, in each graph piece. So we use that information to create our number of atoms and number of bonds tensors. And within the replace features, you specify a feature dictionary. So we use the hidden state feature only and concatenate the number of atoms and number of bonds to generate the context feature. And note that since the add sets and node sets are not used in the replace features function, those remain unchanged. And here's a helper function, which uses Keras sequential API to declare a small feed-forward network. And we are going to use this layer for some of the GNN transformation layers and to initialize for some projections these layers get as input. So here there is two different ways we are applying graph transformations. One is via the graph update function, and the other one is using the standard GNN layers from the models directory. And we basically run num message passing many times graph updates in total. So let's look at this graph update function. This is a Keras layer available from the library, and it receives a dictionary of node set convolutions or node set updates. So we have only one node set, which is the atoms, and we use this node set update function to update the hidden state of the atoms. Node set update is initialized with two inputs. One is a dictionary of add set convolutions, and the second one is a next state function. So the first input is the add set convolutions, and there is a library provided function that you can use for that, which is the simple conv. Simple conv, as the name suggests, is just doing a concatenation of the source and target node states and applies a user provided projection. Here we are also using the sender edge feature. And sender edge feature is the hidden state, and what simple conv does is it also concatenates the edge feature to the source and target node states before applying this message function projection. And for that, we use the dense layer that we have declared above. Then we do some pooling, some aggregation over the target node set, which is the receiver tag here. And note that this receiver tag can also be set to the source endpoint, so you don't have to use the direction as a limitation for how the pooling operation can happen. Also, node set update. The first feature is this dictionary of node set updates, adsat convolutions. So if this was an heterogeneous graph, you could have multiple entries in this adsat convolution. And one other fact that will be helpful for you is you can declare the simple convolution layer and share it among different adsats for an heterogeneous graph. This can be helpful when if it is aligned with the problem you are trying to solve. Also, the shapes of these adsats and their hidden state representations are aligned. And we have this next state function, right? The next state function for the node set update receives a tuple of 3 values. So the first one is going to be the old state of the node set. The second is a dictionary of adsat convolved messages, the convolution output messages. And the third is an optional context state. So we have the next state from concat function available from TF-GNN library, what it does is just concatenates the old node state with the adsat convolution outputs, and finally applies a projection that we have initialized it with, which is a dense convolution that we looked at, and it will return the result. So note that this graph update, right? This graph update transformation just updated our node states in this call. You can actually use graph update to update your ad state as well as your context state. And each of these functions that we looked at has doc strings with lots of examples for you. You can go ahead and learn more about them from their doc string representations. Then there is the GCN and graph sage layers, right? For GCN and graph sage and many other standard GNN architectures, there is some parameters you might want to tune. These hyperparameters can best be tuned using the Vizier TensorFlow Vizier tool that you can use to tune your hyperparameters for better model performance. So now that we have completed the graph transformations, let's get the readout layer. And this is a graph level classification task. So we would want to generate a readout feature at the graph level. So our encoding is going to be at the graph level, and we use this pooling operator at the context to mean pool the hidden state vectors of the nodes, which is the atoms, and get a mean aggregation of those values and assign it to the readout feature. But we also had a hidden state vector for the context, right? So what we would like to do is we will prefer our model to also make a prediction conditioning on the hidden state representation of the context. And how we do that here is by concatenating the graph context's hidden state, right, with the readout features. And before getting the logis layer, we also apply a dense transformation and return back our Keras model with inputs and outputs. So this code block is just calling into the function that we looked at with the hyperparameters listed here. You can go and change and play with these values and see how that will affect the model performance. So the graph tensor spec, right? One other way after you generate your data with the TF data set is this element spec attribute. It will also give you the graph tensor spec. So that's the one we actually used right here to build our model. So in order to compile this Keras model, we also declare the loss and matrix values as well as the optimizer. So here in this block, there is the learning rate decay function applied. If you prefer to, you can also turn it off and see how that will change the model performance. And we compile the model. You can use the model.summary function to look at individual layers in your model, as well as the parameter counts for each and in total. And we train our model for just 200 epochs. We're using 10 steps, declaring 10 steps per epoch. You can change that based on your batch size value. And you can look at both the metrics as well as loss value for train and validation loss. And we have a nicer view for you for this below, which is via the history that we acquired like from the fifth call output. And you can just plot them and look at the loss, binary accuracy, which was one of the metrics we used, binary cross entropy, another metric, and also the respective validation data set results and how it changes throughout our training. So now let's look at a little more advanced topics that we have mentioned is merge batch to components API, which converts a graph tensor with multiple ranks to a scalar graph tensor by merging the different batches in the graph into the connected components of your scalar graph. So here we use a batch size of 5, right? And just take one example of this batched graph. You can see the shape of this is like, there is one in each batch. So in each graph, there is like five different subgraphs here. You can see that in the sizes tensor, as well as the shape of our graph tensor. Now, if you look at the notes at the atom's hidden state feature, you will notice that it's a ragged tensor. And the reason for that is each separate graph in the batch has a variable number of node sets. So in order to represent that, we use a ragged tensor. And also there is the bonds at set, right, with the adjacency structure in source and target nodes. And now, each graph in the batch also has a variable number of at sets. So we also need to use a ragged tensor to represent that. And now let's see how these are going to change after we use merge batch to components API. So after we call this, you can see the shape now the graph tensor shape becomes a scalar shape. And you can see, there is the sizes that also shows, how many graphs have, like this is the representation at the graph tensor level. For the context, there is one context for each graph in the merged scalar graph. And for our atoms node set, now what happened is after merging, right, we have merged also the nodes and the edges, but there is a boundary still between these merged individual graphs. However, we have basically indexed them as if they belong to one scalar graph. So the tensor shape now just becomes, because tensor is a dense tensor, and we can use the full total number of node sets in the scalar graph, which is 85 here, to represent the hidden state feature. And similarly for the edges, we have also put them together. So there is like in total 180 edges. And these components in the scalar graph are not connected to one another. So how do we know the boundaries of that? It's actually via the sizes tensors. So it is most easy, I guess, or most convenient to look at it from the node sets graph piece. So here you can see the sizes tensor now has 5 entries in it, corresponding to each graph in our batch, and also each component in the scalar graph. So the first one has 14 nodes in it, and the second 22, etc. And there, the add set and node set boundaries is going to follow these numbers. So the data set we have used here was for an homogeneous graph. And we have examples in the GitHub repo for heterogeneous graphs as well. So let's take a very simple example, and there is a link to the full collab for the OGBN MAG dataset. So this is the relation. This is the entity relation diagram. And there is, the paper, venue, author, node size and write size, has topic, affiliated with, etc. Ad sets. So you can see a code snippet here, which extends the graph update to an heterogeneous graph, where you have the paper and author nodes getting updated at each graph transformation. So now feel free to look at this student collab. There is a question for you in the student version, which is a simple task to just update the graph or transform the graph update function. So you can also make changes at each transformation to the context state and see how it's going to change the model performance. So you can also play with some of the hyperparameters and see the model performance changing. Yeah, thank you.